Hey, look, it's a bell curve. You knew that had to be coming, right? The official name for this bell curve thing is right here. It's called the normal distribution. So normal distribution means bell curve. And let's just look at some of its basic features, which I think you kind of know a lot of these already. First of all, it's high in the middle, right? It peaks in the middle. And where it peaks is actually the mean value. So you're probably familiar with, somebody giving you the mean and standard deviation on a test, and the mean, of course, is kind of like right in the middle. It's where most people would have scored is at the mean. And the symbol for mean that we're going to be using, that's the Greek letter mu. It's like a Greek letter M, except it's got a longer tail. So it's a Greek letter mu. Looks like a U with a tail, really. Mu. Anyway, so the mean is in the middle. That's one feature. Another feature you'll notice is that it's nice and symmetrical, right? It looks the same on this half as it does on this half, so it's symmetrical. It actually extends forever. I know it looks like it comes right down. It hits the x-axis there, but it actually extends forever both ways, theoretically. So it extends forever. It's nice and symmetrical. It peaks in the middle. Let's see, what else can we say? Oh, you can define like a width. You can define a width. I know it's hard to say. Where do you define, where would you put your vernier caliper on this thing? Well, if you look for something called an inflection point, I'm going to label it IP on the diagram. The word that I'm saying is, or the words that I'm saying is inflection point, okay? And what the inflection point is, notice how it's it's curving kind of like a bowl that's turned upside down, concave down we call this. And then over here, it's like a bowl that's turning up, concave up you might call this. So where the curvature changes from bowl down to bowl up, concave down to concave up, is called the inflection point. It happens right at about that point, and there's another inflection point right about over here, the old IP for inflection point. I'm going to get that out of my way. And if you define that, then all of a sudden you can say, okay, so I'll put my vernier there. This distance right here, this is what we call the standard deviation. And the symbol for that is a Greek letter sigma, which is their version of a letter S. Standard deviation sigma. That's the distance from the middle out to one of those inflection points. So I'm going to label this point mean plus one standard deviation. That gets you to the inflection point. Over here, if you took the mean and you subtracted one standard deviation, you'd get to the other inflection point. And then you'll notice that these points are, that's like add another standard deviation. Here we're going to add another standard deviation. Here I'm going to subtract another standard deviation. Here I'm going to subtract another standard deviation. Okay, so I'm just labeling my x-axis. That would be the x-axis going that way. And then the y-axis, actually we want to be a little bit careful here. Note, y-axis isn't actually probability per se. It's something called a probability density. Let's worry about that later. But I want to get that across because it can actually kind of start messing you up if you start trying to think in terms of, you can't read this like a graph and say, oh, so the probability of that is, read the y-coordinate, right? You can't quite do it that way. It's what this thing is really for. What this for? Bell curve is for what? Bell curve is used for determining probabilities, yes, but it's for determining probabilities in between two values. In between two values. So, for example, if I were to let me just draw a line here at the middle, right? And let me draw a line right about here, okay? If you wanted to know what's the probability of getting a test score, whatever it is, a wombat with a certain height or weight, whatever it is, what's the probability of getting in between here and here? It would be 34%. Okay, that's just a standard feature of the bell curve, that between the mean and going up one standard deviation is 34%. I'm actually going to write it this way. 34% of your area occurs in that little strip right in there. And it's symmetrical, so I think you'll believe me if I say that that's also 34%. Okay, so this is what you use the bell curve for. It's not to find the probability of a particular value, but rather the probability that something is between two values. Between mu and mu plus sigma, in here someplace, it's the 34% area. This area, between the coming out 1 standard deviation and 2 standard deviations here, is about 13.5. This is a little bit approximate, but it's pretty close. 13.5% from there to there. There's another 13.5% over here, 13.5%. And then this area going all the way out is about 2.5%. And the same thing over here. This area going all the way out, not stopping here, but going from here all the way out is about 2.5%. Okay. So this is, how should I say this? I'll just say that this comes up a lot. What if I say it that way? This is amazing how present, ever present it is in so many features of the math world and the world in general. So let's look at a specific example here. Let's look at Bessie, who is a normal cow. Normal meaning that her milk output follows a bell curve. What is her milk output? Her milk output, well, it has a mean of 20 gallons, which is like saying that if you were to map Bessie here, let's put gallons in green, if you were to map Bessie here and draw her bell curve, it would peak right there at 20 gallons because that's her mean output, her mean daily output. And then it says, and Bessie has a standard deviation of 2 gallons. Remember, the standard deviation is this width from here to the inflection point. So that's 2 gallons from there to there, means that that's 22 gallons here. And so you keep going up by 2. There's 24 gallons, there's 26 gallons, and so on. You can keep subtracting 2. There's 18 gallons, there's 16 gallons, there's 14 gallons, and so on. And again, theoretically, it goes forever, all the way to positive infinity gallons, which is not going to be likely, but theoretically possible, all the way back to negative infinity gallons, which again is not likely, but theoretically possible. So notice we can use this information here, Bessie's mean output, Bessie's standard deviation, to label our x-axis, and now we can use this information to answer all of these questions down here. So what do we got here? Under 20 gallons. What is the chance, or I should say, what percentage of days will her milk output be less than 20 gallons? Well, if you look up at this diagram here, and let me erase my smudgies. We don't need those smudgies. Don't need those smudgies. Less than 20 gallons, huh? Well, that would basically mean, let's see, it's a good color. Here's 20 gallons. So 20 gallons or less would be all of this stuff over here, all the way out to negative infinity. So notice the area is going to be, well, you could add 34 plus 13.5 is 44, 47.5 plus this, well, that adds to 50%. Are you surprised that it adds to 50%? Because remember, it's a symmetrical thing, and the 20 is right in the middle, cutting it exactly in half. So actually, it's kind of shouldn't be surprising that half the area is to the left of that mean. Half the area is to the left, half the area is to the right. Which means I just answered the next question. Over 20 gallons. Well, over 20 gallons, just to be official, it would be all of this area. So here's the 20 gallons. Everything higher than 20 gallons is going to fall under this part of the curve. And if you add those all up, you're going to get 50% again. Okay, so it's a nice symmetrical thing. All right, okay. Let's look at something a little more involved. Less than 18. Less than 18. So you come up here, you find your 18. My 18's here. So that less than 18 would be all of these answers, right? Anything to the left of 18. So we want the total area of that shaded part there. And if you can use these numbers to add it up. I had 13.5 there, you add 2.5, you get about 16%. So it's just about 16% of the time her milk output will be less than 18 gallons. Okay, and this is kind of how you play this game. So notice that area under the curve and probability, I'm kind of using those two things interchangeably because, well, they are interchangeable. The area under the curve from here all the way back is 16% of the area is there, and that means 16% probability that if you randomly pick a day, it'll be one of those days, because that's where 16% of the days are. So you can kind of go back and forth. Area, probability, it's the same thing. Next, greater than 18 gallons. Ah, greater than, okay. So again, here's the 18 gallons, we found it. And now you want all the, well, you want to go this way, right? Everything that's greater than, which means you need all of this area from here all the way to the right. And you could go adding this up. You could say, well, I got to take 34 plus 34 is 68. Let's see, 78, 80, 81 and a half, 82, 3, that would be 84%. You could do it that way. Maybe you're noticing that we could have taken a shortcut there. The shortcut we could have taken is to notice that, well, less than 18 was 16%. So greater than 18 would be 100% minus that, because you're either less than 18 or you're greater than 18. You're one or the other. That exhausts 100% of the possibilities. So if it's 16% on one side, it's got to be 84% on the other side. So we didn't even need to add all those things up. We could have just figured that out straight away. Okay, just a few more of these. 18 to 22 gallons. What's the chance, or what percentage of days does Bessie pump out 18 to 22 gallons? Well, here's 18, here's 22, so we're talking about the area between the 18 and the 22. We're talking about all of this area. These are all the days where you get somewhere between 18 and 22 gallons, and you'll notice that it's 34 plus 34 is 68%. Here, why don't you try these three yourself real quick? You can pause, you can unpause. Gives me a little time to fix this. Okay, you back? All right. 16 to 24. Well, we're going to start at 16. We're going to go up to 24. We need all of this area from here all the way up to here. So you add these four numbers. 34 plus 34 is 68. Then you have to add these two as well. You will end up with, trust me, 95%. It might have been a little unfair for me to have asked you to try these two, G and H yourself, but if you did try them, this is gonna stick better because you would have tried it. The 14 to 26 gallons, we're going from, we're going from here to here. And remember what I said before, this is not everything. Everything doesn't go between mu minus 3 sigma up to mu. That's not everything. It extends forever. The bell curve extends forever. So it would be a little bit incorrect if you added all these numbers. By the way, they'd add up to 100%. It's not quite 100%. Really, it's 99.7%. That's a number worth knowing, actually. It's not quite 100%. It's 99.7%. So I guess I should have said that this was like, I don't know, 2.35% or something if you want it to be more accurate. That would go from here. That would go from here to here, and then the 0.15% would be out here. If you'd like to be a little more accurate, you can do it that way. But anyway, 99.7% there. So these three, I want to kind of make a note down here. Notice 18 to 22. We were going from here to here. We were going from the mean, adding 1 standard deviation, subtracting 1 standard deviation. And we got 68%. So 68% of data is, you can say it in words, within 1 standard deviation of the mean, i.e. within, sometimes the short way to say it is this way, mean plus sigma, mean minus sigma. 68% of the data will be within 1 standard deviation of the mean. From part F, we went from 16 to 24. So that was going out 2 standard deviations in each direction. And we got 95% of the data is within 2 standard deviations of the mean, i.e. mu plus or minus 2 sigma. These are the thoughts to link, by the way. 68% is within 1 standard deviation, 95% is within 2 standard deviations, and then part G told us that 99.7% is within plus or minus 3 standard deviations, because we went out to 26 and back to 14. We went up and down 3 standard deviations. So let me get some of this stuff out of here now. It all centers on the mean, right? These are sometimes like given as rules of thumb. These are just some nice numbers to kind of keep in mind. Sometimes they help you just kind of think about where you are in a problem. Say, well, 95% of the time I should be within plus or minus 2 standard deviations. Or, you know. Okay. This part H is kind of a trick question. Not really. I kind of warned you up here, or I didn't really warn you, but I kind of alluded to it when I said the bell curve is used for determining probabilities in between 2 values. In between 2 values. What's the chance that you get exactly 17? 17 is in between what and what? It's not in between anything. It is 17, right? 17 is over here someplace, right? But remember, I was saying this too. You can't just think like, you know, if I read the y coordinate, I'll get the probability. It doesn't really work like that. These aren't really probabilities. They're densities. This is impossible to determine with bell curve theory. You can't determine the probability of some exact amount. You can't do it. You have to have ranges. All of these things are ranges, 18 to 22, over 20, which means 20 to infinity, right? These are all ranges. You can only find probabilities or determine probabilities for ranges of values, okay? So, this page, I feel like I'm going a little fast, but that's okay. You can pause and rewind, right? I think. Anyway, this page is... This is most of it. This is the essential characteristics of the bell curve. This particular shape that we've got here, these particular areas, these particular cutoffs, mean plus or minus 1 standard deviation, plus or minus 2 standard deviations, and so on. These are standard for all bell curves. And like I say, almost everything is a bell curve. You have to know what the mean is. Yep. You have to know what the mean is. You have to know what the standard deviation is. But once you know what the mean is and the standard deviation is, you can label your axis and you can fly. You can go to town. You can figure out probabilities of being between this and this, between this and this, between this and this, and so on. Again, keep these rules of thumbs in mind. They will come up from time to time. Okay, so this, before I go to page 2, this begs the question, of course. Let's see, what color do I want? Let's go with that one. You know, this is all well and fine if you happen to land on these nice numbers like 18, 20, 22, 24. If you have to, you know, if the questions always land on these nice numbers, you're in great shape. But what if you wanted to find the probability of, like, I don't know, 19 or less, 18 and a half or less, in other words, between the numbers? Well, then it gets a little more involved. Still very much the same creature, but we have to get a little more involved. We have to... well, for one thing we have to do is we have to relabel the x-axis. We're going to relabel it in terms of what's called a z-score. So this formula that I just boxed in is the star of this page. Z-score. Notice you take your x-coordinate. This is your Bessie's gallons of milk thing. And you subtract her mean and you divide by her standard deviation and you get what's called a z-score. So if you look at this formula a little bit closely, notice that if she, well, let's do it this way. Let's use numbers. People always like numbers better, right? So I'm going to put Bessie here. You would calculate z-scores by taking the gallons of milk she gives, subtracting her mean, which is 20, and dividing by her standard deviation, which is 2, right? So notice, if she gives 20 gallons, if you put a 20 right here, you're going to have 20 minus 20 is 0. You're going to have a z-score of 0. A z-score of 0 is right in the middle. That's where your mean is. That's always the truth. It's always true. That's the way it works. So notice if x equals 20 gives you z equals 0 is what I was going to write there. But now let me get that out of the way. Notice that if you were to plug in 22, let me scroll back. Remember on this diagram, 22 gallons was right there. It was 1 standard deviation up, right? Add 1 standard deviation. That's how we got to 22. If you plug 22 into this formula, what do you get? You get z equals what? Well, 22 minus 20 over 2 is 2 over 2 is 1. So this corresponds to z equals 1. And to make a long story short, you can continue playing with this formula. And you'll find that this is where z is equal to 2, and this is where z is equal to 3. Here with z equals -1, -2, -3. So the z-score basically counts how many standard deviations you are. It counts distance from mean in terms of the number of standard deviations. So if your distance from the mean, I need a new color. If your distance, I need a new color. If your distance from the mean is 1 standard deviation in the positive direction, you end up at z-score of 1. If your distance from the mean is 2 standard deviations in the positive direction, you end up at z equals 2. If your distance from the mean is 2 standard deviations in the negative direction, you end up at z equals -2, and so on. So it's just it's a shorthand that counts how far you are from the mean in terms of, it counts standard deviations. How many standard deviations are you from the mean? Now let's say that we wanted to, I don't know, let's say, let's do a quick example right here. Find the area left of z, that's area. Area left of z equals, I don't know, I'm just making one up, -0.64. So where would that be here? It would be somewhere around, here's 0, here's -1, so it'd be somewhere over here. So it's kind of hard to get that from our old page 1 diagram, because that only gave us areas, from here to here and from here to here and so on. You had to land on one of these nice numbers. But what if I'm here in between the 0 and the -1? What if I'm at 0.64? What's my probability of being to the left of that? What's my area to the left of that? Well, that's how you use this. That's what this table is for down here. This table gives you all the areas to the left of any z-score you want. Now, the way you find a z-score of -0.64, notice here's z equals 0 right there. So you come to -0.6, and then you have to come over here, because this is your second decimal place, right? So this is -0.60. This is -0.61, -0.62, -0.63. Here's where we want to be, right there, -0.64. And so we can look it up and say, oh, the area left is 0.2611. 26.11% of the area is to the left of that particular z-score. Okay, so that's how we relate any point you wanna, any place you wanna draw a line here. Tell me the z-score, whatever the z-score is. It can be 1, it can be 2, it can be 1.5, it can be 1 1/4, it can be 1.004, it can be whatever you want. Tell me what your z-score is, and I can look up in this table to find out your area to the left. So let's put this into action with some real problems. So let's see now here, let's do this one. Bessie again. She has a mean of 20, she has a standard deviation of 2. We want to know the probability that she produces less than 19 gallons. So this is the x that we're interested in, this is the mu, and this is the sigma. So you calculate the z-score, x minus mu over sigma. So 19 minus 20 over 2, that comes out to -0.50. That's her z-score, or that's the z-score for 19 gallons, I should say. So the area to the left, you come up to this table, Negative 0.50 would be right there, right? You're using the negative 0.5, you're using the 0.00, so it's right there. It's 0.3085. And so the probability is 0.3085, or if you want, 30.85%. The area to the left is 30.85%. That's the probability that you will give less than 19 gallons on any one particular day. So the z-scores kind of let us do any number of gallons. Here's a slightly different problem. It says, what minimum milk output may we expect on 80% of the days? Notice this is a little different because they're not giving us the gallons, they're asking us for the gallons. They're giving us the percentage. So to orient ourselves, 80% of the days, huh? Well, remember if you had the mean, right? Here's the mean. You know that it's symmetrical, so 50% of the days you'll get more than 20. But that doesn't answer this question. We want to get 80% of the days, not just 50% of the days. So that's going to move this over, right? So that 80% of the days is are captured to the right. So that means that this area to the left is 0.20. And you want the area to the left because that's what the table gives you, is areas to the left. So what this problem is basically asking us is to find the z-score that goes with an area left of 0.20. So if the area left is 0.20, I got to come in this table here and I got to look around for where the heck is 0.20 on the inside of this table, and just go until you get pretty close. We don't have to be too exact in this class. And it looks like right about there. That's 0.2005. This is a little further away. Yep. We'll go with that one. So actually it looks like we've got, let's see, cross-reference, negative 0.84. Negative 0.84 would be our z-score. That's the z-score. What's the milk output? That would be our x, right? So I gave you the formula that's at the top of the page that, I gave you the formula at the top of the page that z is equal to x minus, oh, for heaven's sakes, back up. Okay, the z formula goes like this, x minus mu over sigma. If you rearrange that formula, you can get this. X equals mu plus c sigma. All I did is I multiplied both sides by sigma first. That's how I get the z sigma. And then you have to add mu to both sides, so that's why mu ends up there. So this is this is probably a good one for you to keep handy. X equals mu plus z sigma. So we want x. We know what the mu is. Her mean output is 20 gallons. We know what the z is. We just figured out it's, what is it? Actually, it's negative 0.84. And we know what her sigma is. It's 2. And so you just crank that out, and we're getting something like 18.32 gallons. 80% of the times, 80% of the days, you'll get at least 18.3 gallons out of this Bessie cow. So those two examples are kind of like the main two things you do with this table. This is another thing I got to throw at you, and it's what happens if you want to talk about the average over multiple days. So we're talking about getting less than 19 gallons a day. Now we just calculated up here. The probability of less than 19 gallons per day is 30.85%. That's on any one particular day. What's the odds or the chance or the probability that she's going to be doing less than 19 gallons per day on average over a whole week? In other words, 7 days in a row, she's going to average less than. Do you see how that's going to be harder to do? It's one thing to get less than 19 gallons, which is below normal. It's another thing to get below normal 7 days in a row on average. That's going to be a little harder to do. So somehow we expect this to be a different and smaller probability. The question is, how do you get that different and smaller probability? And the answer is this. This has a name, by the way. It's called central limit theorem, which I don't particularly care. I just thought I'd throw that out there in case you end up going to Google sites or whatever and you see central limit theorem. that's where this comes from. Anyway, what you do is okay, let me put it this way. If you're going to do this average over 7 days thing, then when calculating z-score, you want to use not sigma, but this, which is what? Sigma over the square root of n. Okay? You make your sigma a little bit smaller. In this case, since we're talking about 7 days, we're going to use, well, the sigma is 2. We can put that in there. 2 gallons over the square root of 7 days. And so that comes out to, what's that come out to? 0.756. Use that in your z-score calculation. So here we go. Z equals, you go your x minus your mu over your sigma. The x that we're interested in is 19 gallons a day. Her mean was 20. And we have to use this new and improved standard deviation to get our z-score. Okay, so this is the big giant thing. If you're talking about a series of days, and you're talking about the average over that series of days, you have to divide by the square root of the number of days. Take the sigma, fix it that way, make a smaller sigma. The z-score now is going to come out to negative 1.32. And if you look up the area left of negative 1.32, it comes out to be 0.0934, which means it's only a 9.34% chance. Compare that to the 30% that we got up here. It's only a 9 or so % chance that she will average less than 19 for a whole week in a row. So if she does, you might say, uh-oh, she might be sick, because it's not likely that that would happen by chance. So, okay. Now I should note that this z-score of negative 1.32, if I scroll back up, it's kind of off this chart, right? You'll have to look right next to the guided notes. I'm posting a separate file which has this a bigger version of this table on it. So make sure you get that file before you do the homework, the bigger version. Okay, one more example. There's really nothing fantastically new in this example. I just thought it'd be nice to try to consolidate some of this. I got this one example with, what, 5 parts to it? Okay, let's just try to consolidate our info. We're going to talk about the weight of men, and I'm not quite sure if this information is still accurate, but maybe 15, 20 years ago it was accurate, that the mean weight of men, USA men, was 182.9 pounds, and with a standard deviation of 40.8 pounds. Cool. So, what does this ask us? What weight defines the 75th percentile? If you're familiar with the idea of percentile, you'll see that this relates directly to our bell curve chart. 75th percentile means your weight is higher than 75% of all men. That's what a 75th percentile is. So in terms of this bell curve-y thing, remember, if you go right in the middle, the area to the left is 50%, right? But we want more than that. We want more than 50%. We want 75%. So it's somewhere over here, and I don't care how exact I am, but it's somewhere over here. So I'm going to have an area to the left of 0.75. That's what this means to be in the 75th percentile. The area to the left is 0.75. Now you look up the z-score. Let me scroll up to that table. Area left of 0.75. You have to look down here someplace. 0.75. I hope it's in this table. I'm going to say it's right about there someplace, right? Because here's 0.7486. Here's 0.7517. Actually, it's like right in between those two, really. So why don't we call it 0.6? Oh boy, come on, you. 0.675. That's what I'm going to call it. It's between 0.67 and 0.68. I'll call it 0.675. So the z-score is about 0.675. What weight is that? Well, that's where you have to use this formula that I just gave you on the previous page. You can get the actual weight from the z-score by saying, okay, take the mean, 182.9, add the z-score times the standard deviation, and this weight ends up being 210.4 pounds. So if you weigh 210 pounds, you're in the 75th percentile of weight for men. Next question. What weight defines the middle 75%? Okay, that's a different question. Here we were saying 75% up in part A. We were saying 75% was to the left. That's not what we're saying here. We're saying the middle 75%. So you have to somehow, boy, that's a lousy bell curve. Let's try a little bit better. That's a little bit better. The middle 75%, well, that means you're trying to like chop off something in the middle that has an area of 0.75. That would be the middle 75%, right? So how are you going to find this z-score and this z-score? I'll call that z1 and z2, I guess. You're going to need to find these both z-scores. Well, the table, remember, is always areas to the left, so you have to determine what's the area over here. Well, if I got 75% here, that means I got 25% on both sides, which means I got half of 25%, or 0.125 would be my area to the left here, and 0.125 would be my area to the right over here. Cool. So if the area to the left is 0.125, we can look up on our table and get a z-score of, let me scroll up, oh boy, I hope it's on here, 0.125. Oh, look, right there. Perfect. So it's a negative 1.15. Negative 1.15. By the way, over here, if the area to the right was 0.125, that means the area to the left would be 0.875. And I'll let you do this as an exercise, but you will end up with a positive 1.15 z-score. And that's because it's completely symmetrical. So if this is negative 1.15, this will be positive 1.15. Again, the bell curve is perfectly symmetrical creature here. So anywho, now we want to get to our actual weights, mu, and since it's symmetrical, I'll say plus or minus z sigma. So the mean is, what is it, 182.9, and we're going to add and subtract 1.15 times the sigma of 40.8. And when you work this out, you get a range of, if I use one decimal place, 136.0 on the low side, 229.8 on the high side. Next one. What's the probability? Let me change colors. I'm getting a lot of blue here, dark blue. What's the probability that a randomly selected male weighs over 200? Okay, yep. Weighs over 200. Remember, the mean is over here someplace. The mean was 182, I think. Yeah. So 200 pounds is going to be somewhere to the right of that. So I don't know, it's somewhere over here is 200 pounds. That's my x, not my z. I need my z if I'm going to look things up. But anyway, weighs over 200 pounds means really what we want is this area. We want the area to the right of 200 pounds. Well, as usual, you get your z-score first. So the weight is 200 that we're interested in. Subtract the mean. In fact, let me just rewrite that formula for z-score just to be official. Z equals x minus mu over sigma. So the weight we're interested in is 200. The mean is 182.9. The standard deviation is given as 40.8. And what we end up with here is like 0.41 or 0.42. We end up with a z-score of 0.42. So you take that to your table. You take a z-score of 0.42, scrolling up again. Take a z-score of 0.42. It's positive 0.42, right? Yep. So positive 0.42, that'd be here. And you get a 0.6628. semicolon. So the area to the left, 0.6628. On this diagram, the area to the left is 0.6628. Now we wanted the area to the right, so what are you going to do? Well, it's 100% possibilities underneath the whole bell curve. So the whole bell curve has an area of 1, really. So you go 1 minus the 0.6628 to get 0.3372, something like that. I'll just call it 33.7%. So actually about one-third chance that a randomly selected male is over 200 pounds. Okay. This question, what percentage of males weighs over 200 pounds? At 200 pounds gives me deja vu. What did we do here? We had, what is the probability, whoops, don't do that. What is the probability that a randomly selected male weighs over 200 pounds? So this question, we were randomly selecting a male from the population and saying, what's the probability that he weighs over 200 pounds? And the probability is the area to the right, which is 33.7%. Ask yourself, what makes this question different? What percentage of males weigh over 200 pounds? The answer is it's the same question, really. It's just a different way of asking it. The reason it's a 33.7% chance of getting a male over 200 is because 33.7% of the men are over 200 pounds. The areas and the probability and the percentage, that goes together. The area, probability, percentage, all goes together. So that's the same question, really, just rephrased, just phrased in a different, from a different angle or something. Okay, and then last. 10 men go to the doctor. What does it say? No, 10 men get on an elevator. Okay, 10 men get on an elevator. 10 men. That has to jump out at you. Not just one man. If it was one man, we'd be doing all the same stuff that we did up here if it was one man. Or not there, here. If it was one man. But it's not. It's 10 men. So as soon as you see 10 men, you have to think that we're going to use sigma over the square root of n in our z calculation. Okay. 10 men. It's kind of like Bessie the Cow, the average over 7 days. Here it's going to be the average of 10 men. So 10 men get on an elevator. What's the probability that the total weight exceeds a ton? Okay. i.e., the average weight is, well, a ton is 2,000 pounds. So you have 10 men, that's 200 pounds, right? So what they're saying is that for the total weight to exceed a ton, for the total weight to exceed 2,000 pounds, you'd have to have an average of over 200 each, right? Because if the average is over 200 and you multiply by 10, you'll get an answer over 2,000. So the average is over 200 pounds each. That's going to be our x. The sigma we're going to use, sigma, I don't know what you want to call it, sigma prime or something, is going to be take the actual standard deviation, which was the 40.8, divided by the square root of 10 men. We have to use this in our z-score calculation. This comes out to 12.90. Okay, now z-score. X minus mu over this new and improved sigma. We're talking about an average of 200 pounds each or more divided by a mean of 182.9 over a new and improved sigma of 12.9. We're getting a z-score for this problem of 1.33. Once you have the z-score, you can go to the table, look up the area to the left. I got 0.9082. Now we're talking about greater than, so if the area to the left is 0.9, well, let me draw it this way. If the area to the left is 0.9082, because that's what the table tells us, we're actually interested in probability that the weight is bigger, which is to the right. So we actually wanted the area to the right, 1 minus 0.9082. So it comes out to like 9.18%. So there's almost a 10% chance that the elevator is going to have more than a ton. So hopefully it holds more than a ton. I don't know what the elevator's rated to hold. But if it was rated 1 ton, you actually got a 9% chance of overloading it. Good thing they use a factor of safety. Anyway, I hope you've enjoyed our little excursion into the bell curve. Yeah.